Welcome to the Omniscient Technologies webinar on the state of neural machine translation. My name is Andrew Rufner. I'm the CEO of Omniscient, and I'm very pleased to be here with you today and with our esteemed guests, Kirsten Burns, Dr. Philipp Koehn, and Florian Fez, as our guests and panelists joining us today. The webinar is structured into two parts. In the first part, Philipp Koehn will provide insight into the current state of neural machine translation technology from a research and a practical perspective, to help us understand where the research stands, as well as what this means for real-life applications. The second part will be in the form of a panel discussion, with Kirsten Burns and Florian Fez joining the panel together with Philipp to give us insights from an industry perspective. For the panel discussion, we will start with some initial questions we have prepared, but we would like to encourage you to give us any specific questions you have online. We will select a few of them from the list and will attempt to add the rest to an FAQ after the call, which we will publish. Finally, as a last administrative note, I would like to remind everyone that we will record this webinar and we will place the recording online after the call if you wish to listen to it again. With that having been said, and before we start with the presentation, let me briefly introduce Philipp and our guests. Philipp Koehn holds a professorship in computer science at Johns Hopkins University and is the chair for machine translation in the School of Informatics at the University of Edinburgh. Philipp is well known as a leader in the field of statistical machine translation research, particularly in association with the open source MOSES system, which has become the de facto standards toolkit for machine translation in research and in commercial deployment. Philipp is the author of numerous publications, and he received the Award of Honor from the International Association of Machine Translation last year. As Omniscient Technologies Chief Scientist, Philipp refined machine translation technology for real-life use and continuously drives innovation and technological development. Our first panelist, Kirsten Burns, is founder of Burns Language Consulting based in Germany. She started her career as a translation system specialist for Daimler Chrysler, introducing machine translation to the Daimler Chrysler intranet in 1999, before working as a team leader for the BMW after-sales translations team. In 2005, Kirsten started her own company, an independent consultancy aiming at state-of-the-art quality and efficiency for the multilingual information process chain. Kirsten's team caters to the needs of medium to large international companies with a strong interest in lean management and quality control. As an independent company, Burns Language Consulting has no economic ties to any translation or software vendors whatsoever. Last but not least, Florian Fez is co-founder and managing director at Slater, which is an online publisher that makes business sense of language services and technology market, with news on people and deals that shape the industry. Before launching Slater in 2015, Florian was with language service provider CLS Communications as head of Asia, where he was part of the group management during the trade sale to Lionbridge. Now, with the introductions done, I would like to hand over to Philipp. If you have any questions, please feel free to send them to us via the chat form. Philipp, the floor is yours.
Hello, thanks for the opportunity to give an introduction to where we are today with neural machine translation. So I mostly try to explain roughly how it works and point out some challenges that are currently there. Let me start with so this is an overview. I'm first going to talk a little bit about statistical machine translation, and then neural machine translation and paths to deployment. Here's my one slide summary of what the traditional phrase-based machine translation, which underlies most commercial efforts at the moment, looks like. So you have an input sentence here in German. Natürlich hat John Spaß am Spiel, and that is broken up into so-called phrases. Each phrase is mapped into the target languages, but they might also be reordered. This whole process is driven by a phrase table and a language model. There are also various other scoring components looking, for instance, at reordering probabilities. The disadvantages, of this approach is that the phrase translations themselves do not consider context. Obviously, words have different meaning in different contexts, and the meaning can be determined somewhat from the context. And the statistical machine translation systems that everybody's using these days, only the language model really takes context into account, and even that in a very, very short window of just a few words. Another problem is that there's no generalization between words and phrases. For instance, the word cat and the word cats are just encoded as different tokens, and there's no information from cat kind of getting transferred to the word cats. So training data for cat is not used for cats. There's no general principles learned about plurals of words, and so on and so on. I'll now quickly go over neural methods for language. I think it's now for the last 3-4 years that neural network methods have become really popular for language processing. Let me start with a very simple task you might want to solve. If you have the context of 2 words prior and 2 words afterwards, can you predict the word in the middle? So if you have the previous words too big, the big, and the 2 subsequent words barked loudly, can you predict that the word in the middle is most likely dog, because the big dog barked loudly? That's a pretty reasonable sequence of words. So you can try to solve this with a neural network. So you first encode each word in a bit vector, where you basically just have one of the input slots filled, indicating which word that is. So in the first case, the is the second word and big is the last word in that vector. You then have a mapping from that vector to an embedding. Then you have an embedding mapping from these 4 embeddings to a target embedding, and from that you can predict the output word. So the key here is that you have these word embeddings. So each of these arrows you see in that graph you can view as it's a matrix multiplication followed by a nonlinear activation function. So mathematically it's not very complicated actually. So there's something that people got very excited about for these word embeddings. If you project these word embeddings you get for each word down to 2-dimensional space, you get pictures like this here. So words that are very similar to each other have very similar representations. So these are the deep representations of words. Sometimes there's also referred to as semantic representations because they seem to be capturing the meaning of a word. Words that have similar meaning have similar representations. There's even some claims that you can do basic vector arithmetic with these vectors. For instance, the male and female form of words seem to be spaced apart from each other in the space by roughly the same kind of vector distance. So man mapping to woman is similar to uncle mapping to aunt or king mapping to queen. So you could even do some math. If you know how king and king's related and queen's related and king and queen related, you can then figure out that the vector mapping between kings and queens must be similar. Now let me quickly give a rough overview about neural machine translation. This is a very active field of research, obviously, and there are many models proposed. I'll talk about the model that has been now for around a year and a half, been pretty much the standard model for neural machine translation. So here's a very colorful picture. So it starts with, at the top, input word embeddings, and the left and right recurring neural networks, and so on. Let me go through that rather slowly and carefully. So each of these colorful boxes you can think about as a vector of numbers, as we had in the previous examples. So you start with the input embedding. So this is just as in the previous example, a vector where one of the elements in the vector is set to 1 or the other elements are set to 0, indicating which input word is currently present at that word position. So this corresponds to a sentence. These are then mapped into embeddings. So this is the similar principle as I discussed earlier with trying to predict the word in the middle of a context. Here we look at the left context or the right context. Gets a bit complicated. These are called left to right and right to left recurrent neural networks. So, but what happens here is basically you have for each word in the input representation in a highly dimensional vector, about 500 elements, indicating what the word meaning is with the left and right context together. Okay, so ultimately what we want to do with that is produce output words. So we produce output words in a sequence, outputting one word after the other. So output word is predicted similarly, basically the reverse of the process we discussed earlier, by a hidden state embedding on the output side. That hidden state is informed by the previous hidden state, and it's also informed by input context. So you have to basically, here the challenge is to figure out when you predict the output word, what is it predicted from, which are the input words. And what helps with that is an alignment. So you produce at each point, when you produce the output word, an alignment to all the possible input words. So this allows you then to do basically a weighted sum of the input embeddings. So these are all vectors that can be weighted appropriately, and basically the input words that are most relevant to producing an output word get weighted higher. So the benefits of this model is that each output word is predicted from the encoding of the full input sentence. So we have always the entire input sentence available to us. There is an alignment function that maps to a certain portion of the input sentence, but they're basically informed by the entire input sentence. It's also informed by all previously produced output words. These are produced in sequence, and we always condition on what the previous output words were. So basically, whenever you make a decision what the next word should be in the neural system, it uses all available information at that time. Since we're using word embeddings, we now also have generalization of our words. So the word cat and the word cat have similar representations. The word house and the word home have similar representations. So either if it's morphological variants or synonyms, we can learn from training examples of one kind and transfer them to the other kind. So there's several problems with this current approach. One is a limited vocabulary size. So we basically talk here about vector representation of words at the input and the output, where we have very, very large vectors where most of the elements are 0 and only 1 is 1, and you have to do a matrix multiplication from that to the embedding at the input side, or from the embedding to the output word at the output side, and that matrix multiplication grows with vocabulary size. So to address that in today's system, words are typically split up into subwords. So we don't actually have a very, very large vocabulary with all the words. We have the frequent words represented by themselves, but less frequent words are split up into subwords. So typical vocabulary size are in the tens of thousands, maybe 50,000, maybe 30,000, something like this. There are also very, very active research efforts to go further and split up words into characters and have character models of the words. This might be helpful, for instance, for morphological variants that have similar representation on the character level, and maybe you can automatically learn something from that. That's definitely still in the research stage. It's not quite clear if these work out. Observing the output of a neural machine translation system, we can observe that very often, or sometimes the language model takes over. So the output is produced to some degree by the previous words and to some degrees by the input words. And it can happen that then it's mostly driven what the previous output words are. So sometimes you see output of neural machine translation systems that looks like very beautiful language, but is somewhat unrelated to the input. There's also no explicit modeling of coverage. you're basically just hoping that we're going to translate the full sentence, but content may be dropped, content may be repeated. So these are things you see in your MT output. In general, there's a concern that neural MT output often looks very beautiful language, but might not always be related to the source sentence as closely as we would expect. Here's one of the many evaluations of neural machine translation. So what we see here is the competition that we organize every year on news translation for various languages. This chart here is for English German, where a bunch of research groups participated, and we also used some of the online systems that are available and anonymized them. So online B, online G, online F. You can think about the big online MT systems you can use for free. So this chart shows results both in terms of human ranking of the translations in blue scores. So the ranking is relatively similar for my ranking systems based blue score by human judgment. And you see that the leading systems this year were neural machine translation systems for this language pair. So this is definitely a good incremental improvement over the previous systems. So for English-German, we had a lot of success with a syntax-based system that explicitly modeled grammar. And now, for the first time, we see that neural systems are better than that. These results obviously differ by language pair. English-German has received a lot of attention for some reason in the research community, so that's why I'm showing this example. So I want to conclude with a few comments on deployment, where we are currently in bringing these new models to market. So one thing that is nice about the current statistical machine translation that we worked out, a lot of the issues with customization. So for instance, if you have your own terminology or customer data, it's very straightforward to adapt statistical machine translation systems so that the various functions to override the current decisions of the statistical machine translation system. There's various ways to balance in-domain and out-of-domain data, to balance customer data, channel background data. There's straightforward ways to have rules overriding decisions to, for instance, translate dates and units correctly. So even things like matching from inches to centimeters is something you probably don't want to do with a statistical model, but rather with a straightforward rule. The handling of markup tags, which in some applications is a big deal. These methods that have been worked out for statistical machine translation at this point don't really exist yet for neural machine translation. The research focus obviously is just on the core underlying models, and these more practical issues haven't really been addressed much so far. There's a bunch of deployment challenges for neural machine translation. One of them is speed. Mostly actually training speed. So training takes weeks, even on very specialized hardware. So this is definitely slower than training phrase-based systems or even updating phrase-based systems. Decoding is also slower than statistical machine translation. To train these and to a large degree also to deploy these systems, you need specialized hardware. So we're talking about these graphical processing units that cost about $2,000 each. So you need a few of those to be able to train these models and then deploy these models. Google even has specialized hardware that they use to build these systems. Another big problem is that the process is not very transparent. So if you get output that doesn't look right, it's very hard to then go into the system and either find out why did it come up with these predictions or what could be done to fix it. So we have all these high-dimensional vector representations with lots of numbers in it, but it's really hard to then pin down why did it choose this word, what drove the decision to choose this word. So these are all challenges that need to be met for proper commercial deployment. So that's the overview I wanted to give. And we are now moving to.
Thank you, Philip, for this introduction. I think that was very helpful and provided a good overview as to where we stand, what the opportunity is, which I think is very, very meaningful, but also where some of the real-life challenges are when we're looking at real production deployment. So now that we've had this introduction from Philip, who in his dual role, both as a scientist, but as well as the chief scientist at Omniscient Technologies, is aware of both the developments from a scientific perspective as well as the more complex practical problems in practical deployment scenarios. It's time to open up this discussion to our panel, who, given their different backgrounds, will hopefully have a range of different perspectives that will help us get a good and broad view on both the theory, the practice, but then the business side of the application as well as the technology itself. Before I go into the actual panel discussion and start with some of the questions, I would like to remind all of the attendees that you can submit questions online. You've got the ability to submit questions, any questions that you may have online in GoToWebinar. We will collect these, and then towards the end of the panel discussion, we'll start to address some of those questions. So I would like to encourage everybody who's got questions for any one of the panelists to please add those, and then we will certainly address those either during this webinar or afterwards as part of a FAQ. Okay, with that all having been said, the administrative issues dealt with, let's just head straight into it. So I'd like to start with the business perspective first before we head back into some of the more technological questions. And the first question, really, Mrs. Burns, is for you. You've got extensive experience, given your background of working with language service providers and enterprises alike, and I'm sure that the question of neural MT has been mentioned to you more than once over the last couple of months. So from your perspective, do you see any immediate applications for neural MT today? And what, in your experience, really are some of the key success factors more generally when we're talking about MT initiatives in those customer environments that we've just mentioned?
Mm-hmm. Yeah, indeed. Thank you very much, first of all, Philip, for this presentation. It was very insightful to see again how NeuroMT actually works, and it's spooky how easy it looks, although it is rather complicated when you look into it. Yeah, the immediate applications, from my point of view, from my customers, so to speak, are I would say lie in the mix maybe still, because the neural MT technology is not that well known yet, although everyone's talking about it, and it's not quite finished yet. I would like to say, as much as SMT is not, will probably never be really finished, will really be perfect, and it is hard to explain to customers how it works and what the benefits are, because it is very expensive still for them to apply it on-premise, for example, and it also it totally depends on the use case that we're looking at. For example, I could imagine in a large enterprise, I could imagine inbound communication chats between subsidiaries or international teams, maybe, to be done by using neural machine translation. Because Philip said it, you can never be, it looks beautiful, but you can never be quite sure if it is actually perfect or as perfect as it looks, if it really gives you the right meaning of the source sentence. So if you don't have a chance to do post-editing, then you would maybe then at least have a chance to talk about the results if you're not sure about what is being translated in the chat. For publishing purpose, I think it could be very useful for language directions where there is little training data or very rare language combinations, for example, because it is able to to produce very good results with this, as far as I understand. So these are the use cases that people are looking at right now, I think. What still is needed are very reliable business models and business cases for customers to actually build upon if they look at neural MT and understanding this. So this is maybe to try to look at the immediate application scenarios. And the key success factors, on the other hand, for the companies I work with, I think it's a mix. There is a large the expertise is needed, so there's a lack of expertise and experts in these fields of technology, not only NMT, this is also SMT, of course, in the companies. So they have to rely on expert knowledge from external companies like yours, for example, or our expertise. It's a bit the thing, how can we unveil the black box character of this MT technology as far as possible and make it understandable so that the companies can make intelligent decisions. Again, this is not only for neural MT, it stands as much for this as for statistical MT decisions. You were talking about it, Philipp, suitable MT mechanisms like customization mechanisms would be very important for my clients to be able to control in a certain way the output of the machine translation. And we already have these for SMT, but we don't, as you said, have them yet for a neural MT in such an extent. Making results safe, I know we'll probably never be able to, but in a certain error margin, maybe, making them more reliable. And what else did I think about? In a process integration, but this is something that everybody is aware of already. It's the same for all systems you want to employ. Making data safe, that's the cloud discussion. Again, not neural MT specific, and making MT results accessible, which is also a general problem, not only for solely for a neural MT. So these are, I think, the main success factors I can think of.
Okay, thank you very much.
Sure.
Florian, I mean, as an industry observer, we know that Slater and you specifically have been at the forefront of reporting on neural MT and just the general market developments. So given what you've learned over the last couple of months, but also what you've heard on this presentation from Philipp, what's your estimation on the maturity of NMT? I mean, when do you see these deployments really happening in practice? And from your perspective, what do you see as the lowest hanging fruit?
A very good question, and thanks, Philipp, for step-by-step getting me to the actual, kind of a low-level understanding of what neural actually is. So I can only share my very non-technical view, which I think we're at the extremely, very, very early stages of maturity with neural machine translation. I understand that, as Philipp also pointed out, neural networks have been around for a while, I think even decades, but applying them to machine translation, as far as I understand, is barely 3 years old. So in general, I also have the feeling that machine translation and including neural has really been swept up in this massive artificial intelligence and machine learning hype of the last 2, 3, 4 years. And I think this is really helping accelerate the development, as more money and resources are spent on machine translation and neural. And there's also, I get a sense, a new generation of researchers that are going into machine translation and kind of using the language problem as it is as a yardstick to test their machine learning, jobs. So, and also academia is really pushing the research. We actually ran a quick survey on a website called Archive, where such papers are published, and we found that neural went from 0 papers in 2007 to 7 in 14, 9 in 15, and exploded to like 60 this year, right? So that there's a very strong research push going into that field. And for statistical, we're between 10 and 20 papers in the same period. So basically, this shows that there's a lot of energy going into that space. So and this really only happened this year. You also have to remember that we went from 0 to now 4 major deployments of Neural. With, you have Google, you have Microsoft, you have Systran, and recently we also covered the World Patent, the World IPO organization going live with an engine. I might miss one or two here, but those are the big names that have already switched to Neural, and this only over the course of the last 6 months. So this is really a very, very current topic. All those 4 companies I mentioned are pure NMT deployments. But I also, when I spoke to SDL, somebody from SDL last week, and they told me they're going to roll out NMT in the first half of 2016, not only for the MT clients, but also for their tool that's called adaptive machine translation, which is embedded in their translation productivity tool that translators are actually using, right? So it's not just pure MT, but these capabilities are also being put into deployments where they interact with human translators. You also have other human translation, so-called CAT tools such as LIL that they have experimented with the technology, and I'm sure they're going to be following soon. So now, from what we also just heard from Philipp, I mean, there's still several issues to overcome with Neural, that may slow down its adoption for some of the very narrow applications that paying clients or clients that are paying now for statistical need. They need to have, as pointed out before, you need a certain certainty and an error range, right? And those strange mistakes that Neural still makes, and some of those weird omissions or weird translations may are a bit too much for comfort for now. But it's too early to tell. So also the fact that we haven't really seen any of the big language service providers use Neural, except maybe that SDL thing I just mentioned, is an indication that it's really very early days. And Andrew, you mentioned low-hanging fruits. Well, I think we're picking them right now, right? I mean, the low-hanging fruit is Google coming out with a free, Google Translate offering, or Microsoft. But now here really the work begins, right? The customization and fixing some of these more practical errors that paying clients will want. Yeah.
Thanks, Florian. That was certainly very helpful, insightful. It gave me a very different perspective on some of the points that were just discussed. Philipp, I mean, you've been listening in. Have you got any comments at this stage in terms of what you heard from Ms. Burns or from Florian?
Yeah, I mean, that pretty much matches my view of where we are right now. I mean, there's the core technology that just very recently, really just last year or two, has been proven to be somewhat more successful. But the whole transition now to commercial deployment raises a lot of problems that we already addressed with statistical MT, and now we have to address them again with neural MT. I would like to say that generally the deployment, this is still data-driven machine translation, so you still have to do all the same things. You have to have a lot of parallel data, and you have to train these systems. So a lot of the methods that were in place for phrase-based models are still applicable to neural machine translation. And you can expect a similar chain of work that goes into building these systems. But yeah, there are certain minor technical challenges that have to be overcome, like the ones I listed.
Thank you. So, I mean, I think we've sort of established in the presentation as well as the discussion right now that NMT clearly has got tremendous potential to deliver improved quality over SMT, at least depending on the use case, something that we will be addressing in our neural solution next year as well. But if we look at SMT, I mean, SMT came, it still does come at a higher compute cost than rule-based, and NMT, at least at the moment, is even more expensive than that, given the current hardware requirements, something that might change over time. So, Florian, from your perspective, I mean, do you see that as a hurdle to adoption? I mean, you already mentioned that with the use cases that we're currently seeing are really the ones that are out there with the cloud providers. But I mean, do you see cost as a hurdle as adoption, or what's your view on that?
I have to say, it really depends on the quality. I mean, if neural continues to improve, the better the quality, the less the cost will be an issue. Maybe new application areas or new areas where you can actually deploy it open up because you have a bit of a jump in quality, right? Maybe as we said, chat now might actually work, right? Because you can actually have a decent chat conversation with somebody because the quality gets better. And also, I think, we should assume that the sheer power consumption of neural should be dropping over time. I mean, as generally computing costs are dropping, and that the models are getting smarter. I mean, after all, neural only became feasible over the course of the last few years because that processing power became cheap enough to actually try it, right? Or that the processors became fast enough. So I'm sure that's going to continue into the future, and then the costs are going to drop. So, for example, and this was actually an on-the-record conversation I had with SDL's head of machine translation. He told me that he does not see computing costs as a major headache for them. I mean, he said, yes, I mean, they have to deploy a few more service. Yes, it's not free, but it's not something that is a major worry for him at this. So again, I think if the quality is in fact significantly improved, I don't think computing costs will matter much.
Mr. Burns, from your perspective, what's your experience with in terms of cost sensitivity of users of MT, what that means to real-life expectations? So, or more generally speaking, what are some of the key inhibitors of the adoption of MT in the enterprise and in LSPs from your experience?
Mm-hmm. Yeah, I mean, I have to say, obviously, if NMT is going to produce a quality that will excel, that will be so much better than SMT, then I'm pretty sure that clients will also be willing to pay more for this. It just really depends on the proof. The proof is in the pudding. We will have to see what comes out of this. But it looks very promising, so I can imagine that, A. And I can also say that it really, again, for my clients, it totally depends on the use case. If you really need translation speedy, and they have to be very good quality, and you might want to publish them, and you have to post-edit, and you can prove in the end that if you use neural MT, everything will be that much quicker and that much faster, then I'm pretty sure they will be willing to pay for that. It's just a matter of really making them aware and proving it as well, which is sometimes difficult, that these goals can be achieved. So they really need, and I can just say this is what I deal with on a daily basis, they need a business case, and they need to really be assured that when they make this decision, which can be a quite large one, if they don't yet use MT, or if they already have something in place, then that it's a reliable decision and they have a return on invest on this. So it's rather like it's a business process, like every other, if you want to use a new system in your company, or if you want to improve processes. So that's for this part of the question. And on the other hand, key inhibitors, well, they're kind of the opposite of what I said before. What are the key success factors, in a way? There is no business models yet for the enterprises because data's missing, that maybe sometimes cost is missing or training, data amount and type, and there's experience missing. Often my clients would like to have something on-premise because of fear of data loss, data leak. Still, in Germany, this is still an issue. Internationally, I know it is not that much, but it is true for my clients. So cost of implementation might be rather high here because of the storage and cost. And quality issues they're always worried about, obviously, if they want to publish data. And I don't know, I'm not sure. There is not that much benchmarking data available yet, in my opinion. At Taos, they try to gather benchmarking data, and they did so for a while, so there's some for SMT, but neural MT, obviously, since it's just really speeding up, there is not that much there yet, so that is also difficult. Without benchmarking data, you cannot really prove things very well. No internal skills, again. No post-editors in Germany is something that also, again, for all MT processes, but for neural MT might apply the same way. And, yeah, I think these are the main key inhibitors that I can think of. For the LSPs, I want to add something. It's no business model as well in Germany, and no transparency when they use MT, whichever type. So it needs to be a package that is transparent for the client, that they're using MT and what they're using it for, and that it is cheaper if the client uses this type of package or gets this type of package. This is something that is still missing in Germany in many places. So again, here from a German perspective, these are key inhibitors from this side of the world, so to speak.
Thank you.
Mm-hmm.
So we're going to switch to a couple of questions from our listeners. So one of the first questions that, Florian, if you can take that, so I'd like to maybe ask you to take. This one question is, who would be absorbing the cost of implementing NFT? So will it be the end client, the LSPs? Philipp mentioned already some of the engines that we are training are taking 4 weeks plus. So have you got a view on that particular question?
No, that's a tough one. I mean, I guess it depends on how hard the machine translation provider wants to pitch this and how far the runways with this particular client, as with many other projects. I mean, if you're willing, if you see, a 2, 3, 4, 5-year relationship with that particular client, lots of recurring revenue, you better pick up that initial development cost. But if you're not very comfortable that this is going to be a profitable account, then maybe you should overload this off to the client. So I guess it's hard to give a definite answer. Again, depends on the attractiveness, potential attractiveness of the client you're roll this out. And as I said before, I mean, I do think these cycles will come down. I mean, we're at such an early stage. I mean, give it a year or two, and these, the 4 weeks are probably going to be a week or a day. Who knows, right? So this is all going to shorten a lot.
Okay, thank you. Philipp, we've got a question for you. One of the questions was what the added value of Neural MT compared to SMT was, specifically, and what the drawbacks were. If you could maybe take that.
I mean, the selling point, that what really matters at the end is the quality of the translation. So if the translation quality is better, that's certainly a convincing argument. So at this point, there's some indication that you can get better quality translation with your machine translation. It's not quite clear what the conditions for that is. It seems to be that you need a lot of data. You need more data than you usually have for statistical methods. It might also be a bit more domain specific, so you have to make sure that you actually have relevant domain data. So at this point, if you can get higher quality with Neural MT, then yes, you should go for it. But again, at this point, it comes with several drawbacks that you can't customize it as well. You need more expensive hardware and so on. So it doesn't necessarily make a convincing argument at the moment in every given situation.
Okay, thank you. I've got another one that, I mean, I'll leave it open to anybody on the panel to answer that one, but Philipp, I guess this is most likely down your alley. The question is, have the word alignment algorithms been successfully transported to the publicly available cloud engines? And what problems exist in creating a proper many-to-many word alignment, i.e. 0, 1, 2 or more words in the source language can be mapped to 0, 1, 2 or more words in the target language?
So that exists in the neural models to some degree. So I was talking about the alignment step in the middle that is, for historical reason, called attention mechanism. So there is actually some reference of each output words to input words. It's not as we used to kind of crystal clear mapping. It's probabilistic mapping where you say, well, the word translation comes 50% from that word and 20% from that word and 10% from that word, and then and so on. So that is one way you could establish a word alignment between the output and the input. But nothing prevents you also from, when you have the full sentence translation, you just run traditional word alignment methods over that and get word alignments out that way. It's not quite clear at the moment what's the best way to get word alignments for these methods.
All right, thanks, Philipp. We've got another interesting question here, actually, which is, what will be required to integrate Neural MT with translation software, so CAT tools. Again, anybody on the panel, if you've got a particular view, or I don't know, maybe Dion, whether you even want to jump in here at this point.
Sure, I guess I'm a bonus speaker today. This is Dion Wiggins, I'm Omniscient's CTO. Basically, the integration for any tools will be just via the standard APIs. Any of the vendors out there doing MT will be able to obfuscate whether it's SMT rules or anything else. It's just normal, business as usual. So from an external technology perspective, it's going to be very transparent.
So maybe then let me add on to that. Maybe, I don't know, Philip or Ms. Burns, maybe you can take that one. So we've just heard Florian talking about adaptive MT. So when we're looking at MT and now adaptive, you know, how are we going to make those two fit together? Anybody on the panel got a view on that? I mean, it's obviously using the more statistical model as the basis.
Well, as far as I understood it, adaptive MT actually just, which does it, I don't mean it in a bad way. It updates your engine with the results of the post editor, so that the next result will be better because it already includes your correction. So I would think that it would be beneficial to any MT system, although I'm not sure how this will react, how back corrections of MT results will benefit the neural MT engine. Maybe Philip can comment on that. Not sure.
Yeah,
if
so
it
the
will
way
make it better.
I didn't talk at all about training of these models. So these models are trained by just basically feeding one sentence pair after the other into the makeup, and you learn from the mistakes you make on each sentence. So it makes predictions for each sentence, you know the reference translation for each sentence, and you learn from that. So you basically sequentially feed in your training data over and over and over again. Since that's how it's being trained, it's actually then pretty straightforward how to adapt to new training data. You just have to run a few more cycles with this new training data. So that's one way to go about it. I'm not entirely sure if this is going to be the last word of it, because there are all things being done to make them more robust. So, since the training is always very much impacted by the last examples you saw, you overfit them too much. So there are things like ensemble learning to overcome these problems. So you have to address these as well.
Also, training will be, the training cycle is rather extensive today, right? So every sentence that cannot just be fed it back into the neural MT system, I suppose. That wouldn't be efficient at the moment.
Yeah, I mean, the whole training, I think I visualized it a little bit, since there are all these boxes, and between each box matrix multiplications. I mean, now talking about matrices of 500 times 500 or 5,000, or outside vocabulary of 50,000 words. So it is computationally very expensive. So training is not feasible without the GPU. Deployment might be feasible without a GPU, but if you then talk about adaptive, then you basically have to buy into the whole training infrastructure that you need in place.
Okay.
One of the other, I guess, I mean, now you're probably best suited to answer this one, and I think you alluded to it through your presentation as well as part of the comments, but one of the questions that we had here is, are there cases, or could you be a little bit more specific about cases where SMT or rule-based MT is still better than NMT and vice versa?
I think it has to do with data resources. So from what we've learned so far in the research community, you can obviously build a rule-based system if you have absolutely no data at all. So that's probably, if you don't have any training data, that might not be the worst thing to do. We also know that you can build phrase-based models on customer data with just a 1,000,000-word parallel data, or even less than that. And it seems that for neural MT, you definitely need more than that. So it might be that neural MT really only works well if you have massive amounts of training data. I mean, the kind of published efforts of Google or WIPO, I mean, these are situations where you have massive amounts of training data. So that might be one criteria to know what to deploy where. but it's a bit early to say to figure out where one method is better than the other.
Okay. I think you alluded to the training data already, and one of the questions that we got here as well that's related to this is whether you could allude on the differences in terms of the requirements of training data when we're looking at SMT versus NMT.
Yeah, I don't want to say any hard numbers. So I know from efforts, so there's a big US-funded DARPA research project on low-resource languages where you have only a few 100,000 worth of training data, and a lot of high-profile research groups use neural NT for that, and they all failed miserably. So that doesn't seem to be enough. It is enough to build phrase-based systems and hierarchical systems, not necessarily very good ones at least, but at least some that produce somewhat decent output. So for statistical MT, I think the number was always, you should have around 1 million words, otherwise it's not really worth doing. The number might be higher for neural MT.
Can you also allude maybe a little bit to the type of training data? I mean, when we do statistical, for example, right, I mean, 3 elements that are really important to us are terminology, language model, and parallel data, and actually in that order as well. So how does that change when we do NMT?
Yeah, so the NMT models as I set out so far are just be able to use parallel data, so only translated text, which is a bit surprising because a big component of what makes traditional statistical MT work is large amounts of targeted monolingual text from which you can train a lot of a very solid language model to really guide them translations. There is not yet a definite solution how to use large amounts of monolingual data in neural NT. So there are some hacky solutions of just taking the monolingual data and translating it back into the source language and then have artificial training data to train on. But that's a very expensive way to deal with that. There's also not a very clear way how to deal with terminology. So terminology usually means you have a list of terms that have to be translated in a certain way. You don't have the hard kind of mechanisms of a phrase table and restricting translations to a phrase table in neural NT. So there's not currently a very good solution to deal with that.
Okay, thanks. Then another, I think, a pretty good question that we had here as well, and I think I'll leave it open to obviously anybody on the panel to answer this. Is do you think that linguists can be involved and work together with the developers in training the machines in order to achieve better results? Is this something that's happening today already? Any views on that?
Well, as far as I understood, this is not possible with NMT to actually really pinpoint the problem. You can say that there is a problem, but you cannot really then pinpoint the problem in the data. But maybe Philipp can enlighten us on this because I'm no specialist at all.
Yeah, I mean, so in statistical MT, there are certain aspects to building these systems where knowledge about the language helps. For instance, if you deal with morphologically rich languages, it helps to then come up with schemes to break up morphologically complex tokens into morphemes. That's where linguistic knowledge helps. There are also fairly established solutions to have a rule-based reordering component that has been developed by someone with linguistic knowledge of the languages. Yeah, currently the neural NT is not that amenable to kind of fiddling with input or output. But I think it's currently still a very, very open question how to visualize or learn something about how the neural NT system works and where it fails and why it fails. So once we have a bit more insight about how we can basically debug them, then there might be opportunities to then also figure out how do we represent the data differently and what kind of linguistic pre-processing steps might be helpful.
Okay. And then, since we're sort of getting to the end of the hour, maybe just one final question that just came in. The question was whether NMT, in NMT, the translation is actually faster than the other engines. So compared to statistical and rule-based, from a pure speed perspective, what are the differences given the experiences that you have at this point in time?
No, it's definitely slower. So it depends obviously on what kind of hardware you use and what kind of speeds and quality trade-offs you make. But I mean, we've seen commercial deployment speed of disk MT that are definitely 100 or 10 or 100 times faster than current kind of research systems for neural MT even when using GPUs.
That's quite significant. All right. Well, thank you very much, Philipp, Mr. Behrens, and Florian for taking the time to be on the panel with us today. We're unfortunately already getting to the end of the hour, and with that, the end of this webinar. I would like to thank all of the attendees as well for taking the time to attend this webinar. As said, we have recorded this webinar. We will make this available for you to listen to online as well. And we will also post all of the questions and the answers that were asked, both on this call as well as answers to questions that we unfortunately didn't get around to answering on this call as a FAQ post this call on our website, and we will notify you by email of that as well. So with that having been said, again, I'd like to thank you all very much for taking the time. I'd like to thank my panel very much and wish you a very good day. Thank you very much, and goodbye.